In this example, we have multiple objects connected by ropes moving vertically. And so it seems our herpetologist's work is never done. Now these three crates need to be hauled upwards from the loading dock to the housing level. And suppose we are given their three masses and we're given the tension in this rope right here, tension 1. We would like to determine the acceleration of all three crates. And since they're moving as one, they'll all have the same acceleration. And also the tensions in ropes 2 and 3, and then rank the tensions in the three ropes so we can tell which one of them would be most likely to snap. All right, we'll start with our free body diagrams. Clearly, each of the crates should get a free body diagram, but the ropes, how about them? If a rope has a mass that can't be ignored, then you can think of a rope as behaving just like a long, skinny block and give the rope its own FBD. But if, as here, we work in the massless string approximation, then you don't need an FBD for the ropes, just the crates. So here we are, FBDs for the three crates, for C, B, and A. Let's look first at crate A here. There's tension 1 pulling upwards on it, but the easiest thing to miss is tension 2 in this rope pulling downwards on crate A. A rope always pulls at both ends. So if rope 2 is pulling crate B upwards, it's also pulling crate A downwards, like a pair of equal and opposite forces in the massless string approximation. Here that string is pulling B upwards and A downwards, and we have a constant tension in that string. Same tension at either end if we're using that massless string approximation. And so the FBD for B here is similar to that for A. There's tension 2 pulling upwards on B, tension 3 pulling downwards, and then the force of gravity on B as well. They're the weights of our two crates. Crate C has the simplest FBD, just tension 3 pulling upwards on it, and its weight pulling downwards, the force of gravity. Okay, I think we can determine the rankings of the tensions just from looking and thinking about the free body diagrams. We know that if the crates are accelerating upwards, each one must have a net force that is upwards. So tension 3 must be greater than the weight of crate C, for instance. And if this is a massless string, then it's the same tension at this end as at that end. So tension 3 pulling upwards on C is the same as tension 3 pulling downwards on B. And the sum of these must be smaller than this tension here, from 2 pulling up on B. And then that tension is the same here and here, so the sum of these must be less than tension 1 pulling upwards on A. So, all right, I think there we have it. Tension 3 is less than tension 2, is less than tension 1. So we've got our rankings, and notice that we did not say anything about the masses of the crates in figuring this out. This is independent of the masses. It doesn't matter which of these is the heaviest. So we can understand that by recognizing that it's tension 1 right here, this rope, that ultimately is responsible for hauling upwards all three of those crates. Whereas tension 2 here only has to haul upwards crates B and C, and tension 3 only has to haul upwards crate C. So even if this was the most massive crate, this is still the smallest tension because it's only responsible for hauling up that one crate, not multiple crates as the other two ropes are doing. Okay, so there's our ranking. Now let's get our AAA step here, our axes, and start doing some Newton's second law for the individual objects. Here we go, Newton's second law for crates A, B, and C. What I want to point out here is that crate C here at the bottom, at the end of the chain, the object there at the end tends to have the simplest looking free body diagram. Crate A is also relatively simple because tension 1 is a given, so there's only one unknown here. Oh, and acceleration. It's the crate in the middle, or the mass in the middle of a chain, that tends to have the most complex Newton's second law with the most unknowns in it. So that is good to keep in mind when you're trying to decide which equation to use to solve your problem. This one down here tends to be the simplest. Okay, now here's the part I want you to work out, the Newton's second law for various systems. If we combine A, B, and C all into a system, what is our Newton's second law for that system? If we make just A and B the system, or if we make just B and C the system, what is Newton's second law? What are the external forces in each of those cases? And bear in mind that for these combinations, the Earth is not being included in any of those systems. So the Earth is always external to the system, So the forces of gravity, the interactions with the Earth, those are always going to be external forces. Okay. So let's pause the video and set up Newton's second law for each of those three possible systems. Ready? Okay, here's what we got. Let's look here first at the system A plus B plus C. In that case, the only external forces are tension 1 here, pulling upwards on all of them, and then the 3 forces of gravity from the Earth pulling down. Those are 4 external forces here, divided by the total mass. If A plus B is our system, if A and B is our system, then tension 2 here, that's internal, but 1 is external, and 3 pulling down is external. So we would have 1 and 3 as our external tensions and those 2 forces of gravity on our objects A and B. Likewise, if B and C is our system, then 3 would be an internal force, but tension 2 would be external, and then the 2 weights would be external. All right, so there's our N2Ls for the systems. And I think if we look here at this one, we'll see that we have solved for the acceleration of the system in terms of our givens here. It's just our givens right there. So what we've done is use step 1 of our usual process, N2L for a system, to solve first the most efficient way to get the acceleration. Right there. Put it all in the system and use the systems approach to find the acceleration. So we have done that. Now let's try and find tensions 2 and 3. Our procedure recommends that next we look at N2L for just a single object to find what would be an internal force. Tension 2 is internal to the A plus B plus C system, and tension 3 is internal to the A plus B plus C system. So let's find N2L for just an object to solve for those internal forces. So looking over here, let's see, this one, the most simple of our N2Ls, we see tension 3 is right there. It looks relatively easy to get tension 3 by itself. So I've got the algebra on a card here. Let's pick that equation, N2L for just object C, multiply both sides by MC to get to here, then a couple of lines of algebra, factor out the MC, and we get this expression. Note here and throughout, I have used, for the forces of gravity, this. I've replaced each force of gravity with the mass of the object times little g. And at this point, if we're going to plug in numerical values for little g, I want to remind you that by little g, we always mean the positive value 9.8 meters per second squared if we're on Earth. That's positive 9.8. Don't go inserting an extra negative here. Okay, so if we get down to here, and we have already solved for the acceleration of the system over here, if you have numerical values, solve for that A, we could then substitute in that value right here and solve for tension 3, and there we have it. We've got tension 3 now. Back to our equations to find tension 2. We can go to N2L for an individual object and look for tension 2 here, or also tension 2 appears in this equation for the B plus C system. So none of those looks particularly simple. You could pick any one of those 3 to try and solve for tension 2. I kind of picked this one here since we already know the acceleration and we've just found tension 3. We can solve this one for tension 2. So here's the algebra for that. Let's take multiply both sides here by MB to get to this step, and a little bit of algebra, factor out the MB, and if we sub in our numerical value for the acceleration and sub in the value for the force of tension 3 that we just found, you can then solve for tension 2. Okay, so we've got our expressions for all 3 of our unknowns we were looking for, and I suppose I'll leave you with one final challenge. Suppose if you didn't have numerical values, if you just wanted to continue doing the algebra, could you go on to prove that if you make these substitutions just in terms of variables, tension 3 can be expressed like this, and tension 2 can be expressed like that?